started. Welcome to the first session of Friday. It should be a small mistake that I'm introducing my co-author, but anyways, our first speaker will be Sisi Zhou. She will be talking about quantum error correction meets continuous symmetries, fundamental trade-offs, and case studies. Please.
Hi everyone. Today I'm going to talk about the fundamental trade-offs between quantum error correction and continuous symmetries. So, first, we all know that quantum noise is one of the biggest enemies of building a real-life quantum computer. And quantum error correction is an important tool to protect quantum information from noise. And it works in such a way that a bunch of logical qubits are encoded in a large number of physical qubits. So for example, we can take a look at this 9-qubit shortcode here. One logical qubit is encoded into 9 physical qubits. And the decoding channel works in such a way that for any noise acting on this encoding channel, the effect of noise can be completely erased, which means that if the input state is psi in the logical qubit, then the output state should also be psi. So if we take a look at this in the abstract version, we can take a look at this diagram. So suppose we have an arbitrary logical qubit state or any logical state psi, and our goal in quantum error correction is to perform this identity operation on this logical qubit. Then what's happening is that we first do an encoding operation, and there is a certain noise channel we want to correct, and then there is a decoding channel such that the entire error corrected noise channel is equivalent to the identity channel in logical space. So it works very well if we want to know if we want to build a quantum memory. However, if we want to perform useful quantum computing, we also need to perform arbitrary type of quantum gates on this quantum state. So for example, here we can take a look at the situation where we want to perform a logical gate UL on an arbitrary state psi. And then since we are doing quantum error correction as well, what's going on here is that we must design a physical gate that's acting on the physical qubit such that when it is sandwiched by the encoding and decoding channel, the entire channel gives us the logical unitary operation, UL. So we can see from these two diagrams here that if we want to perform non-trivial logical gate operation on psi, then the structure of noise and the structure of the physical gate must be fundamentally different from each other. So this is actually a key observation leading to the proof of Easton-Kneel theorem. So Easton-Kneel theorem is a no-go theorem stating that any quantum code that can correct local errors does not have a set of transversal logical gates, which is universal. So here by transversal, I basically mean the situation where we have like a m-partite system, and then the gates act independently on each of the subsystems. So the entire gate is the tensor product of unitary acting on each subsystem. And we call this type of gate transversal gate, which is very useful in fault-tolerant quantum computing. So in order to prove the Easton-Kneel theorem, we first know that there's this quantum error correction condition, which tells us that given a error correcting code, which type of noise can be corrected. So it actually states that if P is the projector onto the code subspace, then Ki dagger Kj has to act trivially in the code subspace. So Ki here is basically the cross operator of the noise channel, and I could indicate like the index for different type of noise. And from this quantum error correction condition, we can see that if an error correcting code can correct local error, then for any local operator E, it must also act trivially in the code subspace. And then that means if we consider a type of gate which have this form, so we assume that this type of gate is a logical gate, and it is given by this form where we have a local Hamiltonian in the exponent of this operator. then from the quantum error correction condition, we can see that this type of gate must also act as the identity operator in the code subspace, because the generator of this is going to be trivial, satisfying this condition. So as a result, we basically prove that any type of gate that can be written as this form, which is also logical gates, must act trivially in the code subspace. So theta here is basically can be some real number in the neighborhood of 0, and this type of gate actually forms a connected component of the identity in the entire group of transversal logical gates from the group theory perspective. So in that case, basically, if this connected component acts as identity, as we've proven using the quantum error correction conditions, one can also prove that the type of gates can be performed using transversal logical gates must be finite and therefore cannot be universal. So in our work, we went beyond the scheme of quantum computing. Actually, we consider the general trade-off between quantum error correction and continuous symmetries. So basically, we are trying to ask the question if there exists a quantum error correcting code that respects continuous symmetry in the system. So by continuous symmetry, I basically mean the situation where the gate commute with this symmetry of the encoding channel commute with this symmetry operation. So here G is some continuous group, and UL and US are different representation of this group in the logical system and the physical system. And we would say a code is covariant code if it respects this type of symmetry transformation. And the question is, can a code simultaneously be a good error correcting code and also respects non-trivial symmetry operation? And we will see that there is certain conflicts between these two concepts. And we will also derive trade-off relations between the degree of good error correcting code and the degree of symmetry property of the quantum code. So okay, so now let's take a look at the exact setting of our problem. So again, by quantum error correcting code, I basically mean the situation where, given the encoding channel and the noise channel, there exists a recovery channel such that the entire error corrected noise channel would be equivalent to the identity operation in the logical space. And I would use Ki to denote the cross operator of this noise channel. And I'm going to consider U1 symmetry group in this work. And so I'm going to consider the code that respects U1 symmetry, which is called U1 covariant code. And it describes the case where the logical Hamiltonian evolution generated by HL is equivalent to the physical Hamiltonian evolution generated by HS, while theta is just some arbitrary real number. So again, we have this quantum error correction condition to help us determine if the code can correct certain type of noise. And combining these two, we can see that if the physical Hamiltonian is inside the span of Ki dagger Kj, then HL must act as identity in the logical space if the code is simultaneously error correcting and covariant. So however, we don't want a trivial symmetry operation on the logical space. So if we assume that HL acts non-trivially in the code subspace, then this condition must be violated. So basically, this condition, which we call Hamiltonian crossband condition, is a necessary, is a sufficient condition for help us to determine the non-existence of exact error correcting and covariant code. And I also want to remark here, by Hamiltonian, I do not mean the Hamiltonian of the entire physical system. I just mean the charge operator of this U1 group in the physical space. Okay, so we will assume that the HKS condition is satisfied throughout this talk. And it is actually a quite general condition. For example, if you consider the case where K is local operator and the Hamiltonian is also local, then it definitely satisfies this HKS condition. And since we cannot simultaneously have good error correcting code and exact covariant code, we are going to consider the approximate case. So we will use two different parameter, epsilon and delta, to quantify the degree of error correction and the degree of U1 covariance. So basically, epsilon is going to be the distance between this error correcting noisy channel and the identity operation. And in particular, we will use a purified distance, and we are going to minimize the distance over all possible decoding channel to find the optimal decoding channel. And there are actually three types of way to define delta. The first one is called global covariance, which is basically the case where we maximize the distance measure over the entire group, which means we maximize it over all theta. And we could also consider local covariance violation, which basically means that we need to consider the derivative of this distance measure with respect to theta. And one could even consider like the charge conservation, which means which is kind of the difference between the input charge and output charge given a quantum state. So, and in fact, for the sake of time, I'm going to only focus on this global covariance violation in this talk, while the result on other type of definition is contained in our paper. So our main result is that we derive various trade-off relations between quantum error correction and symmetry. So here are the two types of trade-off relation I'm going to focus on. So the inequalities looks complicated, but basically from this expression, we can directly see that it demonstrates the robustness of the incompatibility between error correction and symmetry. So if epsilon is sufficiently small, delta is going to be lower bounded by a positive constant and vice versa. So it means that if you have a error correcting code with a very good property, then you cannot have an exact covariant code, have it as an exact covariant code. So I'm also going to explain the parameters appearing in this inequality a little bit. So delta HL and delta HS basically means the strength of the Hamiltonians, and it is the difference between the maximum and minimum eigenvalue of H. And the J here is actually a complicated expression, but it is related to the saturation of the HKS condition. And F here is actually the quantum Fisher information of this quantum channel with respect to theta. So we're also going to provide code examples that nearly attains the bound in some scenarios, providing evidence that our bound is going to be tight. And I also want to remark here that there are many previous work focusing on the case of the exact covariant code, basically the situation where delta is equal to 0. And we managed to generalize this, resulting to the general trade-off between epsilon and delta. So first, let's take a look at the behavior of these trade-off relations. And as I mentioned, the entire setting of this inequality based on the structure of noise. So we are going to consider different type of noise and different type of Hamiltonian. So we are going to consider first the situation where the system, again, is a n-partite system, and each subsystem is denoted by SI. And then we assume that the Hamiltonian is basically the tensor product of each Hamiltonian evolution on each system. Basically, it's kind of like a transversal gate. And we assume the noise is a random local noise. Basically, it describes the situation where a noise acts on only one of the subsystems, but which is chosen uniformly at random. So in that case, one can try to get a scaling of these parameters with respect to the number of subsystems. So you can sort of verify that J is going to scale linearly with respect to M, and also delta HS is going to scale linearly, and F is going to scale quadratically with respect to M. So then we can see that for sufficiently small delta, epsilon is going to be lower bounded by the scaling of 1 over n. And for sufficiently small epsilon, delta is going to be lower bounded by 1 over the square root of n from the first type trade-off relations, and 1 over n from the second type. So basically, we see that the first type of trade-off relation will give us a tighter bound when we consider this random local noise. And another type of noise that is important is called IID noise. It is sort of a stronger noise compared to the random local noise. So it describes the case where noise acts on every subsystem with a fixed probability, but but it acts basically on the entire system. So it's sort of like more stronger than the random local noise because noise does not act on only one of the subsystems. So in that case, one can verify that the scaling of J and delta HS does not change, but the scaling of F is going to decrease to the linear scaling with respect to N. So in that case, we can see that the lower bound of epsilon is going to be given by 1 over the square root of n from the second type of trade-off relation. And the scaling of delta, the lower bound of delta for sufficiently small epsilon is going to be 1 over the square root of n, which is the same as before. But in this situation, we see that the second type of trade-off relation gives us a better result in terms of the lower bound on epsilon, the QEC inaccuracy. So okay, so now I'm going to talk about one application of our results, which is to provide limitation on transversal logical gate. So recall that we've shown that if we consider this random local noise on one of the subsystem, we would have a lower bound on delta, which is given by 1 over the square root of n. So if we have an exact quantum error encode that has distance at least up to 2, then this situation, this lower bound on delta must hold because epsilon would be 0 in that case. And furthermore, we assume that there's this transversal logical gate acting on the quantum error encode, which have this form. So D is kind of representing the precision of this rotation of HL. So the larger D is, the higher the precision of this HL rotation is. And we can see that if we take D to be like very large, we would have approximately an covariant code because 1 over D is going to be a very small number, and it becomes almost like a continuous application of this gate. So in fact, then one can basically prove that there is a relation between delta and D, which says that the delta times D must be upper bounded by the scaling of n. And combining these two, we can prove that D is upper bounded by the scaling of n to the 3 over 2. So it's basically provide an upper bound on the precision of this transversal logical gate. So as an example, if we consider a stabilizer code, it basically means that the gate cannot, this type of transversal logical gate cannot go beyond O of log n's level in the Clifford hierarchy. So basically it shows that by considering this approximate symmetry property of error encode, it is possible to get a bound on the gate precision using our results. So now I'm going to provide 2 examples of error encode that nearly saturate our bound. So the first type of code is an exact error encode, and it is called quantum Reed-Muller code. So the quantum Reed-Muller code is actually, I'm going to consider this 2-dimensional, which means like we have only one logical qubit, quantum Reed-Muller code, and the code word is going to be given by the superposition of computational basis, which is described by this classical shortened Reed-Muller code. So for example, here we write down the truth table of all degree 1 Boolean function. And if the first digit is 0, it gives us the computational basis for a logical 0 state. And if the first digit is 1, it gives us the basis for the logical 1 state. So this type of code have a very nice property, is that it have this transversal logical gates looking like this. So basically, if we want to implement the rotation of the Pauli Z operator, we can do this up to this certain precision where T can be very large. In that case, we would have an approximately covariant code. So we can compute delta in this case, which is going to be 2 over the square root of n. And it exactly match our lower bound up to a constant factor of 2. So the second example is called modified thermodynamic code, and it is actually a family of codes that interpolate between exact covariant code and exact error correcting code. So in the exact covariance end, basically when we take this parameter Q to be 0, we would have this exact thermodynamic code. And it is actually given by the decay state of a spin chain. So basically, if we consider this n spin chain and use this charge operator as the sum of Pauli Z operator, the decay state is basically the symmetric state, which is the energy eigenstate of this charge. So one can verify that if the state is a decay state, it is actually naturally going to be a covariant code, but it cannot be an exact error correcting code. And we could add this extra term here based on parameter Q, and we can verify that when Q is equal to 1, then the error correction condition is satisfied and the code becomes exact error correcting code. So one can calculate epsilon and delta in this case, and epsilon is going to scale like 1/n, which exactly matches the scaling of our lower bound. And similarly, the scaling of delta is going to be the same as our lower bound. Okay, so finally, I'm going to talk about the proof technique of our two trade-off relations. So in fact, the techniques to prove the two trade-off relations are very different. So in order to prove the first type of trade-off relations, we make use of this concept called charge fluctuation. It is sort of an indicator of whether the code is an exact error correcting code and exact covariance code. So charge fluctuation is defined by this expression here. So it's basically the fluctuation of charge in the logical subspace. And when epsilon is 0, that means when the code is exact error correcting, one can use the quantum error correction condition to prove that chi has to be 0 if the code is exact error correcting. So it's this end. And when delta is 0, that means the code is exact covariant. And one can also prove that chi has to be delta HL, which is positive, because this physical Hamiltonian must be mapped to the logical Hamiltonian if the code is exactly covariant. So we can see that it is somehow an indicator of the incompatibility between the error correcting property and the covariance. So in order to get our trade-off relations, we first try to put a lower bound on delta using the distance between delta HL and chi. And we can also put a lower bound on epsilon using the distance between chi and 0, which is basically the absolute value of chi. So combining these two, we will be able to prove that prove this first type of trade-off relation. Okay, so this is the first proof technique, and the second proof technique make use of a different concept called gate implementation error. So we actually consider the distance between these two gates on the left-hand side and right-hand side. So on the left-hand side, we have a quantum channel, which is a composition of 4 quantum channels: the encoding channel, the physical Hamiltonian evolution, the noise channel, and the decoding channel. And we can see that if the code is covariant and also perfectly error correcting code, then it's going to be equal to the logical Hamiltonian evolution on the right-hand side here. However, if the code is not exactly error correcting and covariant, gamma is going to be larger than 0. So basically, one can show that the sum of epsilon and delta is going to be lower bounded by gamma. And if it is possible to derive a lower bound on gamma, we would have our second type of trade-off relation. So in fact, you can find this lower bound on gamma using methods from quantum metrology. And basically, you can sort of calculate the Fisher information of this quantum channel, and you can show that it's lower bounded by the scaling of 1 over gamma square, and then it effectively put a lower bound on gamma. And combining these two, we would have this trade-off relation between epsilon and delta as our second result. So okay, so to summarize, we've derived several type of trade-off relations between quantum error correction and continuous symmetries. And we also show that the relations are nearly optimal in certain scenarios. And we also provide application of our results in fault-tolerant quantum computing. And there are also other type of trade-off relations based on different symmetry measures that I didn't have time to discuss. And there's also a detailed proof technique based on metrology and resource theory that is contained in our paper. Finally, there is also the potential physical applications of our results in quantum gravity and many-body physics and so on, which is also discussed in our paper. That's all for my talk. Thank you very much for listening.
Okay, thanks for the nice talk. We have some time for questions.
Sorry, one question. So, in this talk, you consider a continuous operation. So I'm slightly confused, but usually in the quantum computation, we only use some discrete parameters, the discrete operation. So why you consider a continuous operation?
Yeah, so so actually the motivation of considering the continuous symmetry does not exactly rooted in quantum computing, because it's actually very important in a specific physical system that respects certain symmetry. So if the dynamic that generates the error correcting code respect the symmetry, for example, if it's like a circuit which is like a charge conserving, then it's going to respect this continuous symmetry. So if there's a charge in the system, it's going to respect this continuous symmetry. But it is of course closely related to this quantum computing case, because in quantum computing case we would also need to apply the logical gates up to a certain precision, and the higher the precision is, the lower the parameter delta is. So basically, if we consider this parameter delta, is also going to tell us a little bit about what's going on in the quantum computing case, but not in the exact way. Yeah.
And also, you consider some hierarchy of quantum operations. I cannot remember, but maybe you show that C1 and C2, C3. So, and C1 is Pauli operation, and C2 is Clifford, and C3 is maybe set of quantum gate. So you consider that kind of hierarchy. So I cannot remember where it is.
I didn't exactly got the question. Can you like repeat it again? Yeah.
You show somehow hierarchy of quantum operations. I cannot remember where it is.
Clifford hierarchy, page 11.
Hierarchy, yes, hierarchy. So, well, I could not understand why you consider that hierarchy, and I could not understand the role of that hierarchy in that context.
Yeah, so I guess it's because like many known example of transversal logical gate have this form. So that's why it is important to consider like this type of transversal logical gate, where basically you put this H to be a constant, and then you consider a family of code where D increases. So D would increases with the number of qubits. So then in that case, it is closely related to the Clifford hierarchy if you consider stabilized code, because basically, the larger B is the higher the Clifford hierarchy you are in. So,
Yes, limitation transversal logical state. So in the slide you consider, yes, this. So your method works with that kind of a higher hierarchy. And that VL. Okay.
Yeah, so basically one example is this quantum reading code. And you can see that basically you are in the first level of Clifford hierarchy. If you can implement it, okay, yeah.
Okay.
Yeah. I also have some comments that I make, but maybe let's take it offline because we already past time.
Okay, I'm fine.
Okay, let's thank the speaker again. So our next speaker is Vishal. Our next speaker is Vishal Singh. Can you share screen?
Yes.
Thank you. So I still cannot. Okay.
I'm sorry.
Great. Okay, so our next speaker is Vishal Singh, who will tell us about quantifying the performance of approximate teleportation and quantum error correction via symmetric 2 PPT extendability. The floor is yours.
Thank you. Hello, everyone. That's the title of my presentation. So just a brief outline. I'm going to talk about approximate teleportation. Then we're going to look at a semi-definite program with which we can estimate the simulation error in the approximate teleportation using 2 PPT extendability constraints. And we're going to use some symmetries to simplify the STP and then connect it to approximate quantum error correction. So the approximate teleportation protocol looks something like this, where Alice has to send a state to Bob, and they share a known resource state, rho A hat, B hat, and they're going to use a channel L to simulate an identity channel with this. So this overall channel N has to be as close to the identity channel as possible, and they're restricted to use only one-way LOCC communication. So L has to be a one-way LOCC channel. Only Alice can send classical information to Bob, and they both can apply local operations. And we're going to quantify the error in simulation by diamond norm. So the error is going to look like this, where A is an appending channel that appends the resource state rho, and L is the one-way LOCC channel that we're looking for. And so eventually what we want to do is optimize over all these L channels and find out what is the minimum error possible given the resource state rho. So so we want to write a semi-definite program for this, but we have a problem that it is difficult to optimize over the set of one-way LOCC channels. To come across this problem, we find a set of channels that can be characterized by semi-definite constraints, because it is something that can be efficiently solved in classical computers. With efficiently, I mean in the dimension of the matrices and not the dimension of the qubits. So to find this set of channels, we demand that the channel be 2 extendable and that the extension be PPT preserving channels. So we know that 2 extendable channels are they contain the set of one-way LOCC channels, and so does PPT preserving channels. And so we want to look at a set that is as small as possible. And then we're going to optimize over this larger set or a relaxation of the set of one-way LOCC channels, and that will give us a lower bound on the exact simulation error. So just a reminder about diamond norm. The diamond distances between two channels is defined as follows, where you optimize over some state psi, and you just see the difference, see the trace distance between the outputs. And this can be calculated using a semi-definite program, which looks like this. And gamma n and gamma m are the Choi operators of the quantum channels. And you just need two different variables to optimize it. And so it is a semi-definite program that can be solved on a classical computer. So we want to add in two extendability and PPT conditions. So it looks something like this. So the original channel had inputs A hat, and B hat, and an output B. Now we want to extend this to another system, which is B2, and we demand that this is permutationally covariant. That means if we swap the inputs and the outputs at the same time, the channel doesn't change. So this channel remains unchanged under this action, and it has it can be described by a semi-definite constraint. The second condition is that it should be non-signaling. That means if we trace out B2, the output from B2, that means we get the original channel. So M is the extension and L is the original channel that we were looking for. So what it means is that B1 or B2, they cannot signal back because we require that the channel is a one-way LOCC. Only Alice can send classical data to Bob. And this can also be written as a semi-definite constraint. So now we look at the PPT conditions for this extension. A channel is PPT preserving if the partial transpose on one of the systems. So this transpose is not a channel. This is just an action, and we demand that this total action is also a quantum channel, that it is a completely positive and trace preserving map. And this can be written as a semi-definite constraint. And we demand that the joint system of both Bobs, that is also PPT preserving. So this also has to be a quantum channel, and it has a simple semi-definite constraint. So now we can write the diamond norm of the, we can write the SDP for the diamond norm with two PPT extendability constraints. This is the original diamond norm SDP, where we have just used the Choi matrix of the identity channel, and this is the Choi operator of the joint channel, where we have appended the resource state row, and this is the Choi operator of the one-way LOCC channel, or rather 2 PPT extendable channel that we're looking for. And these are the additional constraints. This one is the trace preserving condition, which is required for M to be a channel. This is the permutation covariance condition. This is the non-signaling condition, and these are the PPT preserving conditions. So this is the SDP that we can use to estimate the simulation error or get a lower bound on the simulation error. But the problem is that M scales very fast with the dimension of the simulation of the simulated channel, as well as the resource state. So it depends on all these systems, and it becomes very hard to solve this on a classical computer for even simulating a three-dimensional identity channel. So we can use some symmetries to simplify this SDP. We know that the identity channel has this symmetry that if Alice can apply a unitary and send the information of a unitary to Bob, and then Bob can apply the Hilbert-Schmidt conjugate of that unitary, and that channel remains invariant in this condition. Also, we know that the diamond norm is invariant under unitary action. That means if we apply some unitary channel to both the channels that we're comparing, the diamond norm doesn't change. So we apply the sandwiching action to both the channels, the identity remains the same. And what we know is this symmetrized channel, or this new channel, this performs equally well as the original channel. We can average over all these unitaries, and using the convexity property of the diamond norm, we can bring the integral inside and look at the Stoll channel. And what we can say is that the Stoll channel is always going to perform equally or it's going to perform as well or better than the original channel that we're looking for. And so that suggests that the optimal channel has to preserve this, it has to obey the symmetry that it doesn't change in the action of twirling. So we now, to be consistent with 2PPT extendability conditions, we look at the two extension of the twirl channel. So L was the original channel, and we apply these two unitaries. And so its extension is going to look like this. We can easily see that it follows all the conditions that we were considering. And so we can look at the action on the Choi operator of this problem. So L tilde is the twirl, is the Choi operator of the twirl channel. And if the extension of L tilde is M tilde, then this is the Choi operator of the twirl channel, and the optimal channel has to obey the symmetry that it doesn't, and the Choi operator doesn't change under the action of twirling. So this twirling can help us simplify the STP, because you can decompose a twirl Choi operator as follows. M tilde was original Choi operator that depended on the channel, but if it is twirled, then we can get these S matrices, which are constants, and these M matrices are the only operators that depend on the original channel. So we know something about these S matrices. There are 6 of them. S plus, S minus, and S0 are orthogonal projectors, and S0 to S3 are Pauli-like matrices, where S0 acts as the identity, and it preserves the commutation and anti-commutation relations. And so the final STP depends on 6 variables, which is M plus, M minus, M0 to M3. And even though the number of variables are much larger, we have reduced dimension of the variables, and that gives us a computation advantage, as in the code takes much less time to run. And as you can see, it does not depend on the dimension of the simulated channel. So it would only depend on the dimension of the resource states. And here are some numericals. So we considered a resource state of this form, where with some probability P, you have the maximally entangled state, and with 1 minus P, you have a separable state. One of them is a maximally mixed. So a separable state is basically useless for teleportation. And so we compare the bounds that we get if we just use PPT preserving conditions, and if we use 2PPT extendability conditions. And we can see that for low values of P, 2PPT extendability gives a better bound than just PPT conditions. So now we're going to connect this to approximate quantum error correction. The problem of approximate error correction looks something like this: that Alice and Bob, they already have a channel N, and they're allowed to do local operations on that system, and Alice is allowed to send some classical data to Bob, and then they want to simulate an identity channel with this operation. So it's the same case. We can only use one-way LOCC channels, and we again want to quantify the simulation error using time and norm. So the final diamond norm looks like something like this, and D and E are the ones that we need to optimize over to find out what is the minimum simulated error. So it is helpful to use the language of superchannels. A superchannel is a general map that takes a quantum channel to another quantum channel, and every superchannel has a unique CPTP map associated with it. So if you consider the channel N that goes from A hat to B hat, you can apply a superchannel epsilon S that would change. So this whole thing is a new quantum channel, and it has been shown that this can be dissociated in the following form: that you apply an encoder and a decoder, and they are connected with a memory system. So if we take out the channel from the equation, what we see is that this can be rearranged into this form, where you can see this as Alice and Bob being a bipartite system, and it takes A to A hat and B to B hat. And so we call this whole operation as epsilon, which is the CPTP map that we were talking about. So for 2PPT extendable superchannels, we know that if epsilon s is a one-way LOCC superchannel, that is what we're looking for, then the associated CPTP map is a one-way LOCC channel. And this is the same problem that we're looking for. So what we can do is optimize over 2PPT extendable superchannels to get lower bounds on simulation error. So just as the previous case, we are going to optimize over epsilon, and it translates exactly as the problem that we considered in approximate teleportation. On top of that, the unitary invariance of identity channel also translates into the same conditions, and the diamond norm and the unitary invariance of diamond norm also imply that the dual superchannel is going to be optimal. And because of the same relation, we can deduce that the unique CPTP map, or the unique quantum channel associated with the superchannel, it is also optimal if it is equal to its dual extended channel. So epsilon is the superchannel that we're looking for, and this is the action of dualing if we consider all possible unitary, and this will be the extended map, or the extended channel that relates to the dual superchannel. And so because of the parallels with the approximate teleportation case, the SDP is almost the same with only minor differences. And it follows the same map basically. The Choi operator is again the same with the 6 systems associated with it, but it can be decomposed if it is equal to its dual operation. If it is equal to this dual Choi operator, and then we again have the same S matrices, and we reduce the SDP to just 6 variables, but which are much lower in dimension. And here are some numericals that we perform. So we look at the depolarizing channel to see the difference between PPT and 2PPT extendability constraints. So we are trying to simulate a 2-dimensional identity channel, but we use we look at 2 different cases. If the depolarizing channel itself is a 2-dimensional depolarizing channel, or if the depolarizing channel is a 3-dimensional depolarizing channel, but it is being used to simulate a 2-dimensional identity channel. So if it is a 2-dimensional depolarizing channel, then there is no difference between PPT and 2PPT extendability constraints. But if you use a 3-dimensional depolarizing channel to simulate a qubit identity channel, then the 2PPT extendability constraints perform better than PPT extendability constraints, and they give us a tighter bound. So to summarize, we use 2PPT extendability constraints, and we obtain lower bounds on simulation error for approximate teleportation and approximate current error correction. We use the symmetries of the identity channel to significantly reduce computational cost. The symmetry of diamond norm is also included in this, but it is expected that any reasonable error criterion would obey these unitary invariance conditions. And we also find out that the 2PPT extendability conditions give us stronger bounds than just PPT conditions when we are trying to simulate one-way LOCC channels. And one-way LOCC, one-way communication is the key word, because that is why we have the extra non-signaling condition. And we cannot simply say this for LOCC channels. And the future works might involve a systematic analysis of these symmetry conditions. We eventually want to go to KPPT extendability, because for higher the K, the closer we are to the set of one-way LHCC channels. And we would also like to identify a class of resource states that would saturate these bounds. We know some class of resource state that does this for PPT conditions, but as we have seen, that 2PPT extendability performs better for some cases. So it might also be useful to identify a class that does it for KPPT extendability. And it would also be interesting to look at other semi-definite tightening of the one-way LHCC channels that would get us closer to the actual errors. That's it. Thank you.
All right, thank you for the great talk. We have plenty of time for questions. Oh, maybe I can start with one. So I wonder if you have some understanding about how tight these bounds are compared to LCC. I mean, even through numerical cases, or just any understanding.
Yeah, that is one of our next steps, that we want to find out the upper bounds and see how it compares to how tight these bounds are. But we're not there yet, and we're just going to work on it a bit more.
I see. I guess it's related to is it really worthwhile going to like KPPT extendability, something like that, right? Or
yeah, so like 2PPT extendability gives us like a slight advantage over PPT.
yes.
So we're not sure. So like just extending this method to 3PPT extendability is not something that is easily achievable, I guess, because
I see.
Yeah, we don't have like a systematic framework that could do this. We had to these symmetries and these S matrices. If you go for 3-dimensional, then it's just it's going to be a lot of math that is not very easy to do analytically, I think. So we need to find some structure to the problem that could help us get to KPPT.
I see. Okay. Yeah. I just mean the ultimate target is LCC, right? So I'm just wondering if
Yes.
you know how tight it is. Yeah. Good. Thank you. Any other questions? Yeah, I remember from your paper, you have these huge SDPs,
Oh yeah, I
right?
couldn't put them in the PPT, so
Yeah, maybe it's a good idea to showcase them next time.
yeah, perhaps. I mean, I can say about the advantage they give. They're like, for at least when the simulated channel is two-dimensional. Sorry, simulated channel is three-dimensional.
Mhm.
I'm sorry, simulated channel is two-dimensional, and the resource state is two-dimensional. Then it gives an advantage of about 20 times better than the original STP that we're looking for. So yeah, it should scale pretty well when we are considering high dimensional teleportation.
Mhm. Okay, I guess the talk is clear enough. So yeah, if there's not other questions, maybe we should move on, or we should wait.
Yeah, I guess we should move on. Right. Thank you.
Okay, so next speaker is Shenqiang Zhao. Can you share screen?
Michelle.
Hello, can you hear me?
Yeah.
Okay.
So shall we start? Great. Oh, okay. So our next speaker is Shenqiang Zhao. He will tell us about information recoverability of noisy quantum states. Please.
Thank you for the introduction. Hello, everyone. I'm Shenqiang Zhao. Today, I want to share with you this work titled as Information Recoverability of Noisy Quantum States. This is a joint work with Benchi Zhao, Zihan Xia, and Xin Wang. And it was done when I was a research intern at the Institute for Quantum Computing at Baidu Research. The information we refer to here in the title is the shadow information. We know that quantum states are the carriers of information in quantum computing. It not only carries quantum information, but also classical information. And the results we usually want from quantum computing are still classical, like the measurement results of some quantum systems. So shadow information is one kind of classical information. That is the expectation value of some chosen observable. We call it shadow information because you can imagine the quantum states as a 3D objects in the space, like the cone shown here. So if you observe it from top, you will see a triangular shadow. And if you observe it from the left, you will see a circular shadow. So different observations, different observables will give us different shadow information, which corresponds to the different shapes of shadow here. And it is important because the shadow information is target of many quantum algorithms. For example, the variational quantum eigensolver for the chemistry simulation and the algorithms for solving nonlinear differential equations. And both of them can be run on near-term quantum computers. The near-term quantum computers are prone to noise. It results from that the quantum system usually suffer from unwanted interactions with the environment. For example, energy could flow from the quantum system to the environment, which is called energy dissipation. So such noises can be modeled as quantum channels, which are completely positive and trace-preserving maps, or just CPTP maps. And each quantum channel has a cross representation, which is as shown in the blue box. So the operators EK are the cross operators for the quantum channel, and they satisfy this completeness condition. As example, here are the cross operators for the amplitude damping channel, which describes the process of energy dissipation. So we know that during the process of computation, the noise can affect the states of the quantum systems. For example, the cones showing on the left are transformed into a cylinder on the right. And it will also change the shadow information encoding in the states. So if we observe the both objects from the top, we will see totally different shapes of shadows. This means that undesirable quantum channels will corrupt the shadow information and yielding misleading results. On the other hand, if we observe both objects from the left, we will see the same circular shadow. So this tells us that what observable we are using to measure matters. So this example raises the first question we study in our work, that is, when is the shadow information with respect to an observable preserved? To approach this question, we consider from an operational perspective. In particular, we consider the optional task of recovering the faithful shadow information from the noisy quantum states. And we consider within this probabilistic sampling framework. So at first, we have multiple copies of the noisy quantum states. For each copy, we apply a channel sampled from a set of channels, and then measure the states in the basis of the observable of interest. After getting all the measurement results for all the copies, we will post-process to estimate the noiseless shadow information. We use this framework because it combines the general quantum operations and memory efficient way to manipulate quantum states, because we only need to do local quantum operations rather than global ones. And similarly, frameworks have been used in predicting properties of quantum states, as well as mitigating quantum errors. So far, we have covered the problem of preservativity into a problem of recoverability. And for a piece of shadow information to be recoverable, we mean that there exists such a map D, which is a linear combination of the quantum channels, such that when we apply this map D to the noisy quantum states and measure the new state with the observable O, this should give us the same shadow information as we measure the noiseless state in the original case. And if we take the map D here, we call it as a retriever because it retrieved the shadow information we want. And this is described by a permission preserving and a trace scaling map. So by trace scaling, we mean that this map scales the trace of the input operator. Okay, so if we use the adjoint maps of the map D and the channel N, we can rewrite this equation into this form, in the form equation shown below. So if we want this equation to hold for an arbitrary quantum state rho, then we observe that the two parts highlighted in the orange boxes should be equal. So now we arrive at a minimum requirement for a piece of shadow information to be recoverable or equivalently to be preserved. That is, the N dagger D dagger O should be equal to O. So now the question is to ask, when does there exist such a retriever D such that the minimum requirement is satisfied? We first know that if the requirement holds, then the observable O must be in the image of N dagger because we can see the D dagger O as a whole and as the input to the map N dagger. And then the observable O is just the output of it. So O is in the image of N dagger. Now the question is the converse statement also true? The converse statements say that for any observable O in the image of the adjoint map of the noise channel, there exists an Hermitian preserving and trace scaling map such that the N dagger D dagger O equals O. So the main technical difficulty is the trace scaling requirement on the retriever D. And our main results show that this converse statement is also true. So the answer is yes, the converse is true. And this forms a necessary and sufficient condition for a piece of shadow information to be recoverable. That is, the observable O is in the image of the observable space under the adjoint map and dagger. So this provides a full characterization of the range of recoverable shadow information. Now please allow me to illustrate this condition a bit more. So at the beginning, we have the noiseless quantum state rho. And for any observable in the whole observable space, we can retrieve its shadow information. Now, if some noise channels corrupts the states into a noisy quantum states, then for those observable in this brown area, we can still retrieve their shadow information with the help of a retriever D. And the brown area is just the original observable space evolved under this evolution of the N dagger. Moreover, for any observable outside of this brown area, we cannot retrieve their shadow information. So this is a necessary and sufficient condition for the recoverability of shadow information. And the proof to this condition has two parts. The easy part is the necessity part. That is, if the minimum requirement is satisfied, then the O is in the image of N dagger. This is because the map D dagger is still Hermitian preserving, so the D dagger O is we can denote D dagger O by the observable Q, and so O is just the image of the observable Q under the map N dagger. The hard part is the sufficiency part. We need to prove that if the observable is in the image of N dagger, then there must exist Hermitian preserving and trace scaling map D such that this requirement holds. And we suppose that there exists a operator Q that is evolves into the operator O under the evolution of map and dagger. And we construct the retriever D such that the D dagger maps the observable O back to the observable Q. To ensure that D dagger is trace scaling, we split the observable O into 3 cases. So in case one, we have the not fully ranked and not traceless observables. And we use techniques like space segmentation and unit scaling to ensure that the map D is trace scaling. For case 2 and case 3, we did some manipulation to reduce them into case 1 so that we can use the map we construct there. So this completes the proof of the sufficiency part. And in the end, the sufficiency part, what we really proved is that for any 2 observables, there exists a HPTS map such that maps one observable to the other. And so now we have the condition for the recoverability of shadow information. And we know that different quantum channels could have different level of the shadow information preservativity. For example, the quantum channel N1 here, it only crops 1 dimension of the shadow information, because if we observe it from the left, we will see the same shape of shadow. There could also be another quantum channel N2, such that it crops both directions, both shadows from both directions. So now the question we consider is how to quantify this level of shadow information preservation by a quantum channel. And we propose a quantity called the effective shadow dimension. This directly follows from the necessary and sufficient condition we just mentioned. And it's defined as the dimension of the observable space evolved under N dagger. So it's just dimension of this brown area. So remember that if and only if the shadow information can be recovered, if and only if the corresponding observables are in this brown area. So we just take the dimension of this area of this space as the effective shadow dimension. And this quantity is easily computable by using the channel's cross operator. So we first use its cross operator to calculate the channel's matrix representation. Then the rank of this matrix representation is the effective shadow dimension. So now we're giving the operational meaning for the rank of a channel's matrix representation. And based on this effective shadow dimension, we further define a measure called shadow destructivity to measure channel's ability to destroy shadow information. It is defined as the log of the d squared over the effective shadow dimension. So d squared is the dimension of the original observable space. We take the log of this ratio so that the shadow destructivity has some meaningful properties. For one, it is faithful in the sense that shadow destructivity is non-negative, and it achieves 0 if and only if all shadow information can be recovered. It also satisfies additivity. Consider that we have different quantum channels acting on different subsystems. Then the global shadow destructivity is just the sum of local ones. Also, shadow destructivity satisfies data processing inequality, which tells us that if we send the quantum states through more quantum channels, the destruction to the state's shadow information will only become worse. So that's the 3 properties of the shadow destructivity. And now that's for the recoverability part where we have a full characterization of the range of recoverable shadow information. And to retrieve a certain piece of shadow information, there is some cost. And now we consider the question of how to quantify the cost of recovering a piece of shadow information. So recall that our retrieving protocol is a probabilistic sampling protocol. It uses many copies of the noisy quantum states. So it is reasonable to take the number of copies required as a as a measure for the cost. So let's first review the retrieving protocol. So given S copies of the noisy quantum states, for each copy, we apply a quantum channel sampled from the decompositions of this retriever D. And then we measure in the basis of the observable of interest and get a measurement result O. After obtaining all the measurement results, we do a post-processing to arrive at the estimator for the original faithful shadow information. If we further assume that the measurement result O lies within the interval from -1 to +1, then by Hopkins inequality, the probability of the estimation within a certain arrow epsilon satisfies this inequality. So on the left-hand side, we have the probability that the estimation has an error larger than we expect. And on the right-hand side, we have bound to that probability. So by some simple derivations, we will have this formula for the number of copies required if we want to have a certain accuracy of the estimation. It's interesting to note that this number of quantum states required is proportional to gamma squared, where gamma is the sum of absolute values of the coefficients in the decomposition of the retriever. So we can use gamma as a measure for the cost of retrieving a shadow information. And even if we have the information on the quantum channel and observable, the values of gamma can vary. So there are two important factors that affect the values of gamma. First is that a retriever D has different decompositions, and different decompositions will lead to different values of gamma. So it is desirable to find a decomposition of the retriever to obtain a minimum gamma, and we denote this minimum gamma as gamma minimum of the retriever. Another factor is that there could be multiple retrievers that is valid for retrieving the shadow information. And it is also desirable to find a retriever with the minimum gamma minimum. So combining these two factors, we define the retrieving cost of a quantum channel with respect to an observable as the coefficient gamma minimized over all the valid retriever D and all their valid decompositions. And this cost is efficiently computable with semi-definite programming. And the semi-definite programming will also give us the optimal retrieving protocol corresponding to this retrieving cost. So now we present a case study with the generalized amplitude damping channel. So a GID channel describes the process of energy dissipation at a finite temperature, and it has these 4 cross operators. And the task we consider is to recover the shadow information corresponding to the poly X operator from the states corrupted by GAD channels. One can adopt conventional error mitigation methods, which implements the retriever D as the inverse of the quantum channel. But it does not exploit the information about the observable we have. Our method gives the optimal protocol because it employs an observable adaptive strategy. So it uses the information that we are measuring a poly X operator. And as shown on the right hand, there is a figure compares the cost of our method and the conventional error mitigation method. So it shows that our method consistently achieves a lower cost than the conventional method. It implies that our method could be potentially used as an error mitigation method to suppress noise that's common on the near-term quantum devices, and it achieves an optimal cost. Another advantage of our method is that it extends the scope of application of a conventional error mitigation method. So conventional error mitigation method only works for the case where noise is invertible. However, our method could also work in cases where noise is non-invertible as long as the necessary and sufficient condition is satisfied. So to summarize our results, we address the problem of shadow information recoverability by introducing a probabilistic sampling framework for the retrieving shadow information. Within this framework, we arrive at a necessary and sufficient condition for a piece of shadow information to be preserved or equivalently to be recoverable. And based on this condition, we propose a natural, easily computable measure, which is the shadow destructivity for the destruction of shadow information. And it has some meaningful properties. Then we define a measure called retrieving cost to measure the cost of recovering a certain piece of shadow information. It is efficiently computable with semi-definite programming, and the semi-definite programming will also give us the corresponding optimal protocol. For future studies, we think it would be interesting to consider how to combine our results with error correction or error mitigation so that it can be used in practical scenario. Also, we can consider the cases where we don't have the complete information of the noise model, which is usually the case in practice. And lastly, we can consider the connections of our results to the quantum capacity, which measures a quantum channel's utility to transfer a certain type of information. So that's what I want to share with you today. Thank you for your attention.
Okay, thank you very much for the great talk. We again have plenty of time for questions.
I have a question.
Go ahead.
Can you hear me? Could you go back to the background slide? In the background slide, you had images of number 6 there. That'll do. Actually, go down to 7 if you would. Now you're talking about shadow information, and where you're looking at the observables and the shadows that it casts based off of the the state tomography that you have there, I assume, which is inside the cone. Is there a relationship between the shadow information and the classical shadows? I noticed that you had referenced Huang et al., 2020's paper on classical shadows. So is there some, but that, to my understanding, classical shadows is the sampling done randomly throughout the state tomography. So is there a relationship between the shadow information here and classical shadows of the, Huang et al. Has been working on?
Yes, I think the classical shadows, it consists of like a set of the shadow information, right? So like you are using maybe the set of Pauli operators to extract the classical shadows from a quantum states, and you will need to use many Pauli operators and do many measurements so you can get a classic shadow of the quantum state. And here for the shadow information, we just mean a piece of shadow information is just the one expectation value corresponding to one observable, and we are just considering the recoverability of this shadow information. So it's not like a completely description of the quantum states in a classical way.
Okay, I see. So like maybe the classical shadows data set would be like a subset of the shadow information.
Yeah, yes, the classical shadow,
okay,
like a data set.
Okay, and so that makes perfect sense. So now the point of your talk, just so that I was clear on it, is that if you have multiple channel arrangements, multiple mappings through your quantum channels, then this you're looking for channels that produce the same shadow information output, right? Because the shadow information output is classical, right?
Yes.
But I noticed that so the information that's going through the quantum channels is quantum, yes. And then so you're trying to preserve the classical output in the shadow information through different
Yes,
channel
we-
mappings.
Yes,
Okay.
we are using quantum channels in order to preserve the classical shadowing information encoded in the quantum states.
So is there any constraints on your observables? I mean, like, is it constrained to the Pauli matrices, or is there, or is the
No,
observables
no,
pretty flexible?
It doesn't have any constraints.
Oh, that's cool. Okay, wonderful. Thank you so much.
Okay, no problem.
Can I ask a question?
Yes, please.
Yeah. So I was wondering, have you considered the measurement errors, or is the measurement error can somehow be incorporated into this quantum channel?
No, so for now what operations we can do, we consider them to be ideal. So now we only have the states we available are the noisy quantum states, but what we can do them are just the ideal quantum operations. So that we are doing more like theoretical analysis. So for more practical cases, we could incorporate the measurement noise into the framework.
Yeah, thank you.
No problem.
Okay, on the last slide, can you maybe say a bit more about what you mean by combining with quantum error correction and mitigation?
Okay, so like in this case study, we compared the performance of our method with the conventional error mitigation method, right? So it can achieve a lower cost, and it will have a larger scope of application, as it does not require the noise to be invertible. And however, there is also some disadvantage of our method because it assumes that the noise is modeled as a single quantum channel at the end before the measurement. So maybe there are some thoughts needed to combine to make our protocol practical error mitigation one.
Okay.
Can I ask a question?
Yes, please.
Okay, I'm wondering how do you choose the combination? Oh, no, how do you decompose the retriever map D?
How do I decompose the retriever?
Yes.
Okay, so we proved that the retriever can always be decomposed into two quantum channels, and we also proved that the decomposition with two quantum channels can achieve the optimal value of gamma. So it can be decomposed. Decomposition can be calculated with the semi-definite programming. If we just write the retriever D as a combination of two quantum channels, and then the semi-definite program will optimize these two quantum channels.
So you mean that the optimal decomposition only contains two quantum channels?
Yeah, I mean that there is an optimal decomposition that contains two, but there could also be optimal decomposition that contains more quantum channels, but two is enough.
Okay, I see. So, because in some cases, the retriever map may contains the decomposition with negative coefficient, right?
Yes.
So usually you one of the optimal quantum channel is that one corresponding to the negative coefficient. Is it the case?
So yes, the optimal decomposition has two quantum channels, and
One of them is
a positive coefficient. One of them has the negative coefficient.
Okay, and then okay. Thank you much.
Okay, no problem.
Okay, is there any other question? If not, let's thank the speaker again. Okay, great. So let's move on to the last talk of this session. The speaker will be Koji Yamaguchi, who will tell us about Beyond IID and the resource theory of asymmetry and information spectrum approach for quantum Fisher information. Please.
Thank you for the introduction. Today I'm going to tell you about our recent work on the resource theory of asymmetry in the non-IID regime. And the resource theory of asymmetry is a branch investigating energy coherence, and the target of the study is a general asymptotic theory for the limitations on the distillation and dilution of energy coherence. And to obtain this result, we constructed an extension of information spectrum method that is valid for quantum Fisher information, which is the standard measure of energy coherence. So this work is done in collaboration with Tajima at the University of Electrocommunications, and the technical detail can be found in this preprint on ARPI. Okay, so let's get started. First, what is energy coherence? Well, it is a superposition between energy eigenstate of the Hamiltonian with different energy eigenvalues. For example, this resource is mandatory for creating accurate clocks, accelerating quantum operation, and measuring quantities that do not commute with the Hamiltonian. And applications to these topics are out of scope of this talk, so I will not go into detail here. A branch of resource theory theories analyzing the nature of energy coherence is called the resource theory of asymmetry. And I will provide a concrete definition later, but this resource theory is used to investigate the sequence of the symmetry of dynamics and the conservation models. And in any resource theory, one of the fundamental issues is to determine the limitation in manipulating the resource. And there are two important operations, distillation and dilution. And as you may know, the distillation is an operation of extracting as much resource as possible from a given state. And for example, this is important in repairing damaged resource. And dilution is the opposite operation. That is the operation of creating a desired state by consuming as little resource as possible. And in the resource theory of asymmetry, several important results on the resource manipulation are known. For example, the exact compatibility conditions among pure states are derived in terms of energy distributions in these papers. And in a recent study, the asymptotic conversion theory for IID states are established here. And although this result in the IID regime is important, it cannot be applied to a realistic situation where resources typically have complex correlations. And therefore, the conversion theory that is valid beyond the IID regime is essential. And however, resource conversion theory in the non-ideal regime in the resource theory of asymmetry has not been established so far. But in some of other resource theories, such as entanglement theory, non-ideal theory has already been established. And this is done with the so-called information spectrum method. The information spectrum method is a powerful method to analyze the non-ideal regime for problems related to entropies. For example, in entanglement theory, in the non-ideal regime, the entanglement cost and the disturbed entanglement shown to be equal to the so-called spectral Superman and inframan entropy rates, which is denoted by overlying S and underlying S. And I'd like to emphasize that this result holds for any sequence of pure states. Although the information spectrum method is so powerful, it has not been possible to apply it to the resource theory of asymmetry. This is because that a standard measure of energy coherence in the resource theory of asymmetry is quantum Fisher information, which is quite different from the entropy. So to establish the non-ideal theory in the resource theory of asymmetry, we have proposed an information spectrum approach that is applicable to the quantum Fisher information. So there are three main achievements of our study. First, we introduced new quantities, which we term the spectral Superman and inframan quantum Fisher information rates. And they are the counterpart in the resource theory of asymmetry to the spectral soup and in entropy rates. And second, to construct these quantities through the smoothing method, we define the maximum and minimum quantum efficient information. These two have similar properties to the maximum and minimum entropies. And third, to show the properties of these quantities, we introduce the notion of asymmetric modularization for probability distributions. And we show that the exact compatibility among pure states in the resource theory asymmetry is expressed by using an asymmetric modularization relation. And so this is a counterpart in the resource theory asymmetry to the Nielsen theorem in entanglement theory. Okay, so here's the outline of my talk. I have completed the introductory part and a short summary of our achievement. And I will now provide a complete definition of the resource theory asymmetry. And then I will introduce the spectral quantum efficient information rates. And by using them, I state the main theorem, which relates the coherence cost and disturbed coherence to the spectral quantum efficient information rates. And finally, I will provide an intuitive explanation of this result. Okay, so let us begin by identifying state with and without energetic coherence. Consider a system with a Hamiltonian edge. And as I have mentioned, the energetic coherence is a superposition of energy eigenstates with different energies. And therefore, a state has energetic coherence if and only if it evolves by time evolution generated by the Hamiltonian. We call such a state asymmetric state. On the other hand, a state without energetic coherence is invariant under time evolution. So this is, of course, equivalent to say that the state is diagonalized in an energy eigenbasis. And such a state is called symmetric state. So to manipulate energy coherence, let us now consider the transformation of state. And a basic element is an operation that does not create energy coherence in the sense that it transforms a symmetric state to a symmetric state. So this condition is satisfied if a CPTP map E satisfies this condition. And this can be checked as follows. For symmetric state, law, since law is invariant under time evolution, this equation holds. And by using this condition, this also implies that E law is invariant under time evolution. So if the state law is symmetric, then E law is symmetric. And we call such we call such a CPTP map covariant. And based on these ideas, let us now define the resource theory of asymmetry. Of course, as you may know, any resource theory is defined by its free states that can be freely performed and the free operations that can be freely added. The free states that can be freely prepared and free operations that can be freely performed. And in the resource theory of asymmetry, free state is symmetric state and free operation is a covariant operation. And any state that is not free is regarded as a resource state. So the resource state in the resource theory of asymmetry is asymmetric states. And this construction is, of course, the same as the entanglement theory, where entanglement becomes a resource by defining separate state and LCC as free. Okay. And in any resource theory, it is essential to find a good measure to quantify the resource. And in general, quantity R is regarded as a resource measure, is called as a resource measure when it satisfies two conditions. First, it monotonically decreases under the free operation. And second, it vanishes for any free state. In the resource theory of asymmetry, a standard measure is the symmetric logarithm derivative quantum efficient information with respect to the state, a family of states generated by the time translation. And conventionally, by using the eigenvalue decomposition, it can be the explicit form of this quantity is given by this equation. And conventionally, this quantity is simply called the quantum efficient information. And for pure state, the quantum efficient information is proportional to is given by the 4 times the variance of energy. And in general, so this is a quantifier of the quantum fluctuation with respect to energy eigenvalues. So here, as a side note, let me briefly mention about the difference between the resource theory of asymmetry and the resource theory of coherence. Let us now consider a harmonic oscillator system with this Hamiltonian. And let us compare these two states. the psi1 is given by the superposition of the ground state and the first state, and the second one is given by the superposition of ground state and the second excited state. And in the Litho theory of asymmetry with this Hamiltonian, these two states are not interconvertible. This is because that these two states has different quantum Fisher information. And as I have mentioned, the quantum Fisher information is a Litho's measure in the Litho theory of asymmetry. So if these two has different quantum Fisher information, then they cannot be, they are not intercompatible. On the other hand, in the Litho theory of coherence, with not let us consider the Litho theory of coherence with respect to the energy eigenvalues. And of course, there are several different formations for the coherence theory, but here let us use the so-called maximally incoherent operation as a free operation. So this is a set of all channels that maps diagonal state to diagonal state with respect to some specific basis. And with this definition, it can be easy to see that all covariant operation is okay. It's a maximally incoherent operation, while the opposite is not true. And in the Litho theory of coherence, these two states, and the psi1 and psi2 are intercompatible, since the operation of exchanging the first excited state and the second excited state is maximally incoherent operation. So to summarize, a crucial difference is that in the Litho theory of asymmetry, we care about the energy eigenvalues in addition to the energy eigenbases. But in the Litho theory of coherence with respect to this basis, we only care about the basis. So this makes the analysis of the Litho theory of asymmetry complicated. Okay. So now let me clarify the setup of convergence theory in analysis. And hereafter, for simplicity, we assume that the Hamiltonian of the system is given by the Harmonic-Cauchy Hamiltonian. And it can be shown that the convergence theory for Harmonic-Cauchy system in a pure state can be generalized to any system in periodic pure states with an arbitrary Hamiltonian. So here I provide an intuitive explanation how this works. Suppose that we have a pure state which has a finite period tau with respect to a Hamiltonian x. And let us first discrete the Hamiltonian by multiplying tau over 2 pi so that the state has a period 2 pi. And in this figure, the solid and dashed line represents the energy level of this rescaled Hamiltonian. In particular, the solid lines shows energy level that are included in the support of the state psi. And by using the fact that the state psi has a period 2 pi, it can be shown that the energy gaps for these solid lines are integers. And to obtain the Harmonic-Cauchy Hamiltonian, we first eliminate the energy levels outside the support. And in addition, we add energy levels so that all energy gaps become 1. After this operation, we obtain Harmonic-Cauchy Hamiltonian. And it can be shown that such an elimination and addition of energy level does not affect the convertibility if we only change the energy level that lie outside the support of state. So in this sense, Harmonic-Cauchy Hamiltonian is a standard Hamiltonian to analyze the convertibility among pure states with finite periods. So hereafter, I will always assume that the Hamiltonian is given by this equation. Okay. So now we will analyze the asymptotic convertibility with vanishing error in the asymptotic region. And we adopt the trace distance as a quantifier of error. And we say that a sequence rho is convertible to another sequence sigma by covariant operation, if and only if there exists a sequence of covariant operation that maps state rho to a sigma with vanishing error in the asymptotic region. And in this case, we denote rho hat succeeds sigma hat. And we introduce two key quantities, the coherence cost and the disturbed coherence. And they are the optimal conversion rates from and to reference state, which is defined by these equations. And here we adopted coherence B as a reference, which is given by the superposition of the ground state and the first excited state. And phi hat R is a sequence of coherence bits where a positive number R describes the rate at which the number of coherent bits increases. And in the IID regime, as I have mentioned, these two quantities have been calculated, and it is known that the coherence cost and the disturbed coherence for pure state is given by the quantum Fisher information. However, in general, these quantities does not necessarily coincide with each other, and a general formula for these two quantities in the non-IID regime is the main target of our analysis. So here, for later convenience, we introduce several notations. First, for given pure state psi, its energy distribution is denoted by peak psi. And in the convergence theory, energy distribution plays a key role since any pure state is reversibly convertible to this state, which implies that the convertibility can be fully characterized by this energy distribution. So I should have write peak psi here. Sorry about that. And for sequence of numbers, we define the convolution product by this equation. And for given sequence Q, we say that another sequence Q tilde is an inverse sequence if it satisfies this equation, where delta denotes the Kronecker delta. And so this is the inverse with respect to the convolution operation. An important thing is that such an inverse sequence can be constructed explicitly by using a recursive formula, which I am not showing here, but if the support of the sequence is bounded below. And as we shall see later in analysis, the inverse sequence for energy distribution plays an important role. Okay. So the last key element to construct the information spectrum method for the quantum Fisher information is the generalized Poisson distribution. For a real number lambda, we define p lambda by this equation. When lambda is non-negative, it is an ordinary Poisson distribution. On the other hand, when lambda is negative, this is not a probability distribution, since it becomes negative when n is an odd number. Nevertheless, it turns out that this quantity is of fundamental importance since p lambda tilde is given by p minus lambda. Okay. So now we are ready to construct the information spectrum method. We introduce the maximum and minimum quantum Fisher information for pure state by this equation. And intuitively, these two quantities gives the amount of energetic coherence in psi that can be transformed from and to a pure state whose energy distribution is given by the Poisson distribution. And I will come back to this point later. And also the maximum, we extend the definition of the maximum quantum Fisher information for a general state by using other infimum over the purification of the state. And also, this point is also explained in later. And these two quantities, I mean the maximum and minimum quantum Fisher informations, have similar properties to the maximum and minimum entropies. For example, they give us an upper bound and lower bound for the quantum Fisher information for any pure state. And by using these two quantities, we now define the spectral, supermum, and infimum quantum Fisher information rates by these equations. Here, Fmax epsilon and Fmin epsilon are defined by using epsilon balls. And for maximum quantum Fisher information, we use the ordinary epsilon ball. But for minimum quantum Fisher information, we use the epsilon ball for pure states, since we have defined minimum quantum Fisher information only for pure states. And it should be noted that our definition for the spectral quantum Fisher information rates are very similar to the spectral entropy rates expressed with the smoothing method. In the smoothing method, we introduce a smoothing parameter epsilon, which roughly speaking quantifies the error. And from the minimum and maximum entropies, we can define the smooth maximum and smooth minimum entropies by the equation. And the spectral entropy rates are defined as the asymptotic rates with punishing error. So this is the reason why we call these overlying F and underlying F at spectral quantum efficient information rates. So by using these two quantities, the main result of our paper is stated as follows. For any sequence of pure state, the distributive coherence, the coherence cost is given by the spectral Superman quantum efficient information, while the distributive coherence is given by the spectral infimum quantum efficient information rate. And in fact, this result shows the correspondence between the resource theory of asymmetry and the entanglement theory. In the resource theory of asymmetry, the central quantities are the quantum efficient information and its variant. But in the entanglement theory, various entropy plays essential roles. Although the quantum efficient information and entropy are quite different, our result shows that the convergence theory in the non-ideal regime has a similar structure, both in the resource theory of asymmetry and the entanglement theory. Okay, so now to provide a rough sketch of the proof of main result, I will further explain the detail of analysis. And a key notion is asymmetric modularization. For a given probability, for given two probability distributions P and Q on integers, we say that P asymmetrically modularizes Q if and only if the convolution of P and Q tilde is positive. And in this case, we denote P succeeds Q. And it is shown that the such a modularization relation is a preorder. A key property of this modularization relation is that the necessary and sufficient condition on the convertibility between pure state by covariant operation is given by an A modularization relation of energy distributions. So this is a counterpart of the Nielsen theorem in entanglement theory, which states that the exact convertibility by LOCC is given by the modularization relation of the Schmidt coefficient. So by using the A modularization, I will now explain the interpretation of the maximum and minimum quantum efficient information. We define the maximum quantum efficient information by this equation. The condition we impose here is the A modularization relation. So we can rewrite this quantity in this way, where chi lambda is a pure state whose energy distribution is given by the Poisson distribution. Since the variance of the Poisson distribution is lambda and the quantum efficient information of pure state is 4 times the variance, we get the expression in the last line. So this means that the maximum quantum efficient information is the minimum amount of energetic coherence quantified by the quantum efficient information in chi lambda that is required to create a pure state psi. And similarly, the minimum quantum efficient information is given by this equation. So this means that the minimum quantum efficient information is the maximum amount of energetic coherence that is required, that can be extracted from a pure state psi. So this, based on this, essentially, so based on these observations, we can show that the spectral and infimum, spectral, Superman and infimum quantum efficient information rates capture the coherence cost and the distributive coherence. And of course, the detailed proof is more complicated, so, but I will not present it here. So for technical details, please check this paper. And before concluding my talk, I will finally comment on the cost of creating mixed state. So to be specific, let us analyze a minimal cost that is required to mix state law from a pure state chi lambda. Since the partial trace is a covariant operation, it is easy to see that the cost required to creating a purification phyllo is greater than the cost of creating the state law. And furthermore, by using the covariant Stein-Spring dilation theorem, we can show that the infimum of the cost of creating the purification of law is less than or equal to the cost of the state law. And I think I will skip the detail here, but what is important is that based on this result, we see that the cost of creating law is equal to the minimum cost of creating the purification of that state. So this is the reason why we define the maximum quantum efficient information for a mixed state by using the purification. And essentially based on from the same reason, it can be shown that our result for the coherent cost for pure state can be extended to a mixed state. So that is the coherence cost for any sequence of state is given by the spectral Superman quantum efficient information rate. This is defined by this equation. Okay, so here's a summary of my talk. We have established conversion theory in the non-ideal regime in the resource theory of asymmetry for pure state by using the spectral soup and in quantum efficient information rates. And as I have mentioned, the result for cost can be directly extended to a general sequence of state. And to construct these two quantities through the smoothing method, we define the maximum and minimum quantum efficient information. And we introduce the asymmetric modularization relation. And by using this notion, we have shown we have provided an interpretation of the maximum and the minimum quantum efficient information. And the important thing about the asymmetric modularization is that it gives a necessary and sufficient condition for the exact compatibility among pure state, which is a counterpart to which correspond to the Nielsen theorem. Okay, that's it. Thank you for your attention.
Okay, thank you very much. Questions?
Yeah, I have a question about your definition in the case of mixed state. So in the paper, the way I define it is in terms of the cost for preparing state rho is in terms of the rate of consumption of pure states in the same frequency.
Yes.
And I explained that why purification. If you think about the purification, it won't be the optimal strategy. Basically, to minimize the variance, if you want to minimize the variance, you obtain the purification which will not be periodic in general. So I guess I'm confused about why you define Fmax. Or so why do you define cost in terms of purification? Like why you don't take the the standard definition in terms of the rate of interconversion from pure states to the mixed state rho?
Do you mean that maybe I think I should explain this part in more detail? Is that?
Yeah, maybe. Yeah, I mean, just this definition. I mean, why usually in resource theories the way we define the cost, is in terms of the rate of interconversion from pure state to your fixed pure state to the desired state rho. So, but you're changing that definition, right? Is that you're not
well,
standard definition?
You mean that maybe I think you're suggesting that instead of this definition, we may use just this one as a definition, even for mixed state. Is that your point?
I mean, I'm just suggesting, usually we define it operationally in terms of the minimum rate of resource that you need to consume to prepare the copies of those states. Okay. And I studied that, in the IID regime, I studied that for, and I calculate, and I showed that this would be quantum efficient information of that mixed state rho.
Yes.
But it looks at here, you are using a different definition for mixed state rho. You're just saying, let's look at the purification of rho as the cost. Is my understanding correct or?
Well, so I think your concern is the definition for the maximum contribution information for mixed state, right?
That's right.
Yeah. So we just wanted to make it consistent with the pure state, and we thought that an important thing about the I mean, I think your suggestion is that we can simply extend the Fermat's law by using this situation, right?
Well, I'm suggesting why we don't just think about the standard operational definition in terms of the rate of consumption of pure resource states. Why we change the I'm just asking me. I couldn't understand, I guess, from your talk.
Well, I think so. I think I understand, but our motivation is to I think so that kind of definition is also fine, but if you define in an operational way, in the sense of that the minimum consumption of the resource to construct a state by covariant operation, then so the definition includes something about the existence about the covariant operation or something like that, right? And
Correct.
In that case, it is quite difficult to compute such quantities because we have to explicitly construct the covariant operation for each state or something. So that's something we wanted to avoid. So we wanted to make everything in terms of protocol which can be calculated, at least in principle.
I agree that it will be difficult in general. I did the calculation for IID, but I agree that it will be difficult in general. But that's the standard way of defining the notion of resource cost. It will be a difficult calculation, but I suggest maybe we don't change the standard definition just because it could be confusing for the audience.
Right. I think so the left-hand side of our main result is an operational definition. So these quantities are operationally defined by using the conversion, right? And we want to make it to a more quantities that can be calculated at least in principle, rather than mentioning about the existence of covariant operation or something like that.
But the issue with this definition is that it doesn't give the IID result that in the IID result I showed that you get quantum Fisher information of rho, but if you look at the purification, then you get a larger number than quantum Fisher information of rho. It will be in general larger. If I understand correctly, you are preparing the purified version of the state. Is that right?
Yes.
Okay. And in general, if you use that strategy, I discussed this briefly in the paper, but if you use that strategy, the cost will be higher than quantum Fisher information.
So do you mean that this result is invalid?
I'm not sure if I understand this result, but what I'm saying that in the IID regime, if you use just purification, if you instead of preparing copies of rho, you decide to prepare, if you decide to prepare purification of rho, and there's just some subtlety here, purification of rho that have the same period because you want to use U1 results basically. So if you impose this constraint that I want to prepare purification of rho that have the same period, then in general, the cost will be higher than what you obtain from quantum Fisher information.
All right, so that's why we take the inhuman. So in general, of course, creating a purification of a state is higher than the cost of creating a state, the state law. But what we are saying is that there exists pure state whose cost is equal to the cost for the state law.
Perhaps we discuss this later offline, but I think if you impose the U1 constraint, in general, the cost will be higher. If you want to get a periodic state, it will be larger than Fisher information, but maybe we can discuss it later.
Thank you.
Thank you for the talk.
Thank you very much.
Any other questions? Well, if not, maybe this is it for the first session of Friday. Thanks to all the speakers and thank you all for coming. We'll see you in the next session.
Thank you for a nice talk. So, speaker, please send your presentation file to this address. And also, if you want to continuously discuss, please use one of breakout rooms. So, I already opened 4 rooms.
Thank you. Thank you for organizing this.
Thank you. I'm going to
Koji, do you want to continue?
Yeah, I'd love to.
Okay, if
I
let's
will
go.
move to the first room.
Yeah, okay.